When we talk about vectors, we ultimately get down to talking about the angles that the vectors make and breaking it down into component forces. So let's review the dot product because that has to do with the vector angle. If I have two vectors and I dot them, again, multiply the x-coordinates, multiply the y-coordinates, and I get a scalar answer, not a vector. That answer tells me something. Because if those two vectors are dotted and give me 0, I have orthogonal vectors. We use that to help break our vectors down into its components, its x and y direction components. So a question we might pose is, are these two vectors orthogonal? They're asking for a dot product. So I multiply the x-coordinates, multiply the y-coordinates, and I add the result. If I get a 0, they are orthogonal. If I get anything else, they are not orthogonal. So I can answer no to this question. Another example, I multiply the x-coordinates, I multiply the y-coordinates, and I add them up. I do get 0. Those are orthogonal. Those forces are working at a 90-degree angle of each other. Other thing we talk about is the angle between those two vectors. So here's a way of finding the angle between those two vectors. And of course, we would have to do the inverse cosine to whatever we get here. But we have a dot product of our two vectors, and we have the magnitude of those individual vectors. So I did an example where I dotted out the vectors. 4 times 3 is 12. 3 times 5 is 15. Dotted, I get 27. So they're not orthogonal. They're not going to be 90 degrees. The magnitude of u, so I squared the 4, I squared the 3, I added them up, and I square rooted, and I get 5. The magnitude of v, square the 3, square the 5, add them up, I got 34, square root that, not as easy as the 25, so I leave it as is. And now I do the dot product, divided by the two magnitudes that I got. So this is my numerator, there's my denominator. I do the inverse cosine to get the angle. It looks like these meet at about a 22.2 degree angle. If you are very visual, think about what this would look like. 4, 3, and this is 3, 5. So I'm looking at the angle between those two vectors. Another example down here. If I set it up the same way, I want to dot these, so I get 3 plus 0, that's 3. The magnitude of this one is going to be 3. The magnitude of this one is going to be the square root of 37. I multiply those, and I have to do the inverse cosine of that fraction, that decimal, and this is going to be an angle of about 80.54 degrees. So if I draw out this vector, I get that angle. And I know it's not an orthogonal or a 90-degree angle because I didn't get 0 when I did the dot product. If I did, I could stop and say they're 90 degrees. Now let's look at a couple of examples where we break things down into its vector components. A typical vector component problem will have some sort of object sitting on an inclined plane. And the force, we're talking gravity and weight, of that object goes straight down, but we break those forces into something that's going into the inclined plane, which of course the inclined plane pushes back. That keeps it from falling in. And then we have a force that pulls it down the incline, and we have to come up with an equal force to keep it from sliding down the incline. So an example here would be a 200-pound wagon sitting on an inclined plane of 30 degrees. That 200 pounds goes straight down. I need to break this into component forces. So what's nice about this is this angle in my triangle is the same as this 30-degree angle. That angle gets projected onto this triangle right here. So we now have a 30-degree angle here. So if I take my weight, my force of 200 pounds, and multiply it by the cosine of 30, that gives me one of my forces. If I take the 200 pounds times the sine of 30, that gives me my other force. And you'll notice that x is here and y is here because of the way this gets projected into this triangle. So I'm not looking for this force. This force, when I multiply it out, I get 173.2 pounds. That's how much of the weight is going into the inclined plane and how much the inclined plane is pushing back. I'm looking for the other one because I'm trying to keep this wagon from going downhill. So I take 200 times the sine of 30, and I get 100 pounds. That's how much force is going down the hill. That's how much force I have to exert to pull that wagon back up the hill. So let's take this semi problem. 36,000 pound semi sitting on a 10-degree incline. And we want to come up with the force that's needed to keep this truck from going down the hill. We're not talking about overcoming that. We're just trying to maintain that force. So we need to calculate this right here. So we're going to take the 36,000 and we're going to multiply it by its two components. One of the components would be cosine of 10 degrees. One of them would be the sine of 10 degrees. Now, if we're trying to keep this from going down the hill, if I reference my previous problem, we're looking for that y value because my 10-degree angle is now sitting right here. So this force that's pulling it downhill is the y, x is the inclined plane pushing back. I have projected 10 degrees up to my triangle. So I'm interested in this force right here. It's 36,000 pounds, there's a zero there, 36,000 pounds times the sine of 10 degrees. And I want to know what's going to make that keep the truck from going downhill. So I'm going to do this calculation and I'm going to get 6,251.3 pounds. Significantly less than how much the truck weighs. So to give you a reference, if you've ever seen a strongman competition where they pull a semi or pull a truck or pull a vehicle, they're not pulling the full weight of the vehicle, they're pulling a percentage of it based on the incline and the angle that they're dealing with. The last thing we're going to talk about is we're going to talk about work. Work requires something more than just the magnitude of the force. I can push on my board as much as I want. I'm doing no work because work requires a distance to be traveled. Something has to move. So when we talk about work, we're talking about the magnitude of the force and the distance it traveled. The interesting thing about this, how this ties into our vector components, if the constant force that's being applied is not directed along the line of motion, then we need to do this a little differently. So an example is in order here. We've got our barn, the door is open, and we've got a rope attached to the door that we're going to pull. We're going to exert a force of 50 pounds. The problem is we're not pulling that rope directly in line with the motion. This door is going to move in this horizontal direction, but I'm pulling the rope, some in the horizontal, some in the vertical. So I'm going to have to adjust for this angle of my rope, and I need to know how far this door is going to move if I'm going to do work. So here's the triangle we're dealing with, 50 pounds of force, 60-degree angle, and we're moving 12 feet. So the first thing I need to do is figure out my force. Since we're looking for the horizontal, we're looking for cosine of 60 times the 50 pounds of force. This is my force in the x direction. I don't care about the y direction because the door isn't moving in the vertical. I take that times the 12 for the 12 feet that it moved. So 300 foot-pounds is what I got when I did this calculation. 50 times cosine of the angle, 60 degrees, times how far it moved, I got 300. Now the label is kind of interesting for work because work is a force over a distance. So we're going to take the pounds in my force in the feet in my distance, and we're going to list this as 300 foot-pounds of work. There was definitely a force being applied in the y direction, but the door didn't move in the y direction, so there is no work. You can't have work without a distance traveled.